Welcome, this is Dr. Plague, and today I'll be continuing on with part 2 of designing and building the Plague Mark II homemade CPU. Now if you watched part 1 of this video, then you've noticed that I left us with a bit of a cliffhanger. So let's do a quick recap, and then we'll continue on from where I left off. By the end of part 1, the Plague Mark II was able to execute 4 different CPU instructions: halt, no op, out, and add. The add instruction simply took whatever value was entered into some input switches and added that to the instruction's operand before storing that value into register A. I showed that the add instruction worked by writing a short program with 3 instructions: no op, add 3, and finally a halt. When I entered the value of 2 into the switches and ran the program, we got 3 plus 2, which is 5, and that was stored into register A. Then I removed the no-op instruction, which then made add 3 the first instruction in memory. This should not have changed the result of the program execution, since a no-op doesn't do anything other than to waste a clock cycle. But, as we saw, the program no longer gave us 2 plus 3 as a result. The simulator gave us a result of 0. Then I tried it on the actual hardware, and after a reset, register A held the value of 3 instead of 0. Other than that, it executed the same as in the simulation. Register A did not change after the add instruction was executed. So now, let's see if we can figure out why we got the results that we did. And after we understand that, we'll create a simple fix which should solve this issue. What we need to do is understand how the add instruction actually works. What does the CPU do when it executes the add instruction? Well, there are some things that need to happen for the add instruction to execute properly, and these things need to occur in a certain order. We have a 4-bit adder, and it needs 2 inputs. The adder works asynchronously. It does not need to be connected to a clocking signal. The result from the adder is stored in register A, which needs to latch in the result after it is calculated. Register A is connected to some type of clocking signal, and it latches during a low to high transition of the clocking signal. So the order that things need to occur in are as follows. We need both inputs to the adder to be present. Then there will be a slight propagation delay while the adder prepares the result to show up on its output pins. After the result is output from the adder, register A needs to clock or latch in that result in order to store it. Then the instruction pointer will be incremented to the next address in order to execute the next instruction. This will be the full instruction cycle. The clock signal to the register comes from the 3 to 8 line decoder. That signal will go high when the add instruction is presented on its inputs and the enable pins are set properly. In this case, the main clock needs to be low to enable the decoder. Since the register is latched on a low to high clocking transition, we need the decoder output to go high during the middle of the add instruction. The decoder needs to be enabled during the second half of the add instruction. This means that the main clock needs to be low during the second half of the instruction. And that kind of tells us that the clock needs to be high during the first half of the instruction. The high to low transition of the main clock will latch the result into the register, and the low to high transition of the clock will increment the instruction pointer to the next instruction. So, for the instruction to properly execute, we first need the operand sent to the adder, which requires the clock to be high. Then we need the result latched into the register, which requires a high to low transition of the clock. And finally, we need to increment to the next instruction, which requires a low to high transition of the clock. This means that the proper execution of an instruction for this CPU requires the main clock to start out high. Let's try a little experiment on the breadboard. I'll apply power, and we get a random value in register A. Now, to start out with a high on the clock, I'll just single-step the clock like this. Notice that the clock is now high, and we still haven't executed the program yet. Next, I'll reset the CPU, and notice that both register A and the instruction pointer have been cleared to 0. That's because the clock is high before disabling the decoder. I'll set the switches to a value of 2 and run it. Now we get 5, just like we expected. Now let's figure out what happened during the simulation. The clock started out low, and the first clock transition was from low to high. So when we started the simulation, the clock was low, and that meant the decoder was already outputting a high to the clocking input of the register. The register never saw a low to high transition on its clocking input. The result from the adder was not stored. The main clock then transitioned from low to high, which disabled the decoder and incremented the instruction pointer to the next instruction. Therefore, the register never stored the result of the addition. And now we are on to the next instruction, the out instruction, which ended the program. That's why the simulation showed 0 as the final result. But what about the actual hardware? Why did it give us a result of 3? If you'll notice, when I first powered up the CPU, I did not have any of the value input switches pressed. In fact, I'd never pressed a value input switch until after I reset the CPU. When I pressed the reset switch, it cleared out both the instruction pointer and register A. What it also did was disabled the decoder. As I held down the reset switch, that provided enough time for the first instruction at address 0 to appear on the outputs of the flash memory chip. This means that the operand value of 3 was provided to the adder from the flash memory chip. And since I wasn't pressing any of the value input switches yet, the adder was adding 3 to 0 and providing a 3 on its outputs. Also, since the reset switch is pressed, the decoder was disabled, providing a low on all of its outputs. The reset switch is connected directly to the clear pin of the IC for register A. So as soon as I released the reset switch, that register IC was taken out of reset. The main clock was already low, and since the reset switch was released, the decoder is enabled, providing a high from output number 1 due to the add instruction. But what we need to remember is that there is a propagation delay from when the decoder was enabled to when the decoder output a high on its output pin. The register IC was taken out of reset when the reset switch was released, but the decoder IC needed a propagation delay before it went high, so that gave the register enough time to clock in the output from the adder, which was 3. Then, from there, the clock never transitioned from high to low during the remainder of the add instruction, so the value of 5 never got stored. This is another example showing how simulations can be a bit different from actual hardware, since the simulation software doesn't always simulate propagation delays properly. But, in any case, what we learned is that we need the first clock transition after a CPU reset to go from high to low. Do you think this means we could get this program to work by just adding an inverter to the clock signal? This would make the clock signal start out as a high, and it would go from high to low during the first transition. Let's try it. I'll take one of the unused inverters and send the clock signal into it like this. Then I'll just set these switches to a value of 2. And let's run it. That did work, and we got 5 on the output. Let's try this on the breadboard. I'll just unground this inverter input. Then I'll move the clock signal over to the input of that inverter. Then I'll connect the output of that inverter to the clock line of the CPU. I'll apply power and test it out. And we do get 5. So, is this our solution, to just invert the clock signal? Actually, no. This is just a band-aid to get the first execution to work. Let's try resetting the CPU and see what happens. And I'll make sure to press the reset switch when the clock is high this time. And it failed. Oops. The solution to this problem is not that we need an inverter, but rather we need to synchronize the reset signal to the clock signal. We need to make sure that no matter when we release the reset switch, the CPU stays in reset until the clock has transitioned to a high. Is this common? Do other processors need to synchronize their reset lines to the clock? And let's look at the datasheet for the Intel 8088 processor. If we look at the reset pin in the pin description table, it says reset is internally synchronized. Let's find something a little more descriptive. Look at this. The reset input is internally synchronized to the processor clock, so it's not uncommon to synchronize signals. But how can we synchronize the reset line to the clock signal? It's actually not that difficult. Let's look at what needs to happen. First, let's create a little black box here. It'll have 3 pins on it: the reset input signal, the clock signal that we want to synchronize it to, and a reset output signal, which will be the fully synchronized reset signal. To reset the CPU, we need to bring the reset input low, and then release it back to a high to take the CPU out of reset. So, when we bring the reset input signal low, we want the reset output signal to also go low. But here's the catch. We don't want the reset output signal to go high directly after bringing the reset input signal high. We want to wait until the clock signal transitions from a low to high before bringing the reset output signal high. So, the reset output signal stays low as long as the reset input signal is low, but never goes high until the reset input signal has gone high, followed by a clock transition from low to high. I'll bet we could accomplish this with a simple D-style flip-flop that has a clear input. We can just send the reset input signal into the clear pin of the D flip-flop. This will ensure that the output of the flip-flop will be low whenever the reset input signal is low. So we can use the output from the flip-flop as our reset output signal. And if the flip-flop has both inverting and non-inverting outputs, we want to make sure to use the non-inverting output. Then we can just connect the D input of the flip-flop to VCC while connecting the clock signal to the clock input of the flip-flop. Now, the flip-flop output cannot go high until it sees a positive going transition from the clock signal. By the time the reset output goes high, the low to high transition of the clock signal has already transpired. Therefore, we'll always start the CPU with a high clock signal, and the first clock transition will be from high to low. Let's try this out. I'll add a 7474 dual D flip-flop right here. And since there are two flip-flops in this IC, I'll just use the one on the left side. These D flip-flops have both a clear and a preset input. And since we don't need to preset it, I'll just tie the preset input to VCC on pin 4. I'll also connect the D input to VCC on pin 2, like I showed earlier. And the clock signal needs to connect to the clock input on pin 3. I'll disconnect the reset line from the CPU and connect it to the clear input of the D flip-flop, pin 1. And finally, I'll send the non-inverting output from the flip-flop on pin 5 to the internal reset line of the CPU. This will be the reset synchronizer for this CPU. Okay, let's try this out. I'll set the input switches to 2, and we need to start the CPU in a reset state, so I'll just press the reset switch before running it. I'll add in an automatic reset circuit a little later, which will always reset the CPU during a power-up. Okay, let's run this. And I'll release the reset switch when the clock is low. Now it works, and we get 5 for the result as expected. I'll reset it again and release the reset switch when the clock is high this time. And it still works. Perfect! Since we know that simulations are not always all-telling, let's make sure it works on the breadboard. I need to make room for more ICs by adding another breadboard. So I'll just move this clock source breadboard out of the way. Here's another breadboard that I'll use to finish assembling the Plague Mark II CPU on. And I'll just move the breadboard with the clock source over here. I know, it's pretty sloppy to have power routed over it, but, you know, whatever works. I'll reconnect the clock source to the power rails, and remove the inverter we just added from the clock signal. Then, let's connect the clock source back up to the clock line in the CPU. I'll add the 74HCT74 dual D flip-flop to the new breadboard, then add power and ground. I'll connect the clock signal up to the clock input on pin 3. Then I'll tie the preset input on pin 4 to VCC. I'll send the reset switch to the clear pin of the flip-flop, which is pin 1. The D input on pin 2 will be tied to VCC. Then I'll send the output of the flip-flop on pin 5 to the internal reset of the CPU. I'll just terminate the unused inputs of the second flip-flop to VCC. Let's add power and ground to this new breadboard. And before I forget, let's add the 0.1 mic bypass cap to this new IC. Good enough. Okay, let's reset it. And, yeah, that works. We get 5. Now let's reset it while the clock is high. Still works. And it doesn't matter what level the clock is at when I reset it. It works just fine. Now we do have a second flip-flop on the 7474, so let's put it to use. Whenever we have an asynchronous input to a clocked system, we could experience something called metastability. This is a condition that can occur when a signal, such as the reset input signal, changes at the same time as the clock signal. Meaning, let's suppose the reset input signal is pulled low, then it starts going back high at the exact same time that the clock signal tries to clock in the D input. If the reset input is at an intermediate voltage level, then it can be unpredictable as to what value will be clocked into the flip-flop. You can also run into a situation where the output of the flip-flop is at an intermediate state for an indefinite amount of time. This can cause issues if not accounted for. Actually, there is no known way that I know of to completely eliminate metastability. Let's take a quick look at this book I had back in college. It states, the best that can be done is to reduce the probability of metastable signals to an acceptably low value, such as once in 100 years. We can send the signal through additional flip-flops to help reduce the probability of metastability. So, let's use that extra flip-flop for this purpose. In reality, metastability is a very uncommon occurrence, so don't get too hung up over this issue. I've never seen any of my designs enter into a metastable state that I'm aware of, so this isn't usually a big issue, but for larger designs the probability can go up. So what I'll do here is pass the original output of the flip-flop through an extra flip-flop, into its D input and out of its non-inverting output. Then I'll just carry over the clock and reset input signals to the clock and clear inputs of the second flip-flop like this. This will require another tick of the clock for this reset signal to get through this reset synchronizer. But now it'll be virtually impossible to have a problem due to metastability. The reset input will clear the outputs of both flip-flops. Now we know that even if the clock goes high at the same time that the reset goes high, it won't matter for the second flip-flop since its D input is low. Either way, it'll clock a low to its output. The problem can occur during the second positive transition of the clock. Let's suppose the output from the first flip-flop is metastable. If it remains metastable until the second positive transition of the clock signal, then we're clocking in an intermediate voltage level, which could now cause metastability on the output of the second D flip-flop. The problem would happen if that output remains metastable until the clock goes low again. Then we could be starting the CPU during a low clock signal, which is what we don't want. But the probability of that exact set of events occurring to cause this problem is so astronomically low that we really don't need to worry about it. So I'll leave it at 2 flip-flops. Okay, let's add in the second flip-flop. I'll just connect the reset switch to the clear pin of the second flip-flop, pin 13. Then I'll connect the clock to pin 11, which is the clock input of the second flip-flop. And of course, I want to tie the preset input, pin 10, to VCC. Then I'll connect the output of the first flip-flop through the second flip-flop on pins 12 and 9. Okay, let's test this out. And I'll start the CPU in a reset. Now let's release the reset when the clock is low. And it works fine. Then I'll try releasing reset when the clock is high. And again, it works fine. We just need one extra clock cycle from the previous version, but that's fine. We wouldn't notice it if we ran this at full speed anyway. And like I always do, let's test this out on the breadboard. I'll just unterminate the inputs that we'll be using on the second flip-flop on pins 11, 12, and 13. I'll leave pin 10 connected to VCC, which is the preset input. I'll just move the output to the second flip-flop and connect the first output to the D input of the second flip-flop. Then I'll tie the clear inputs together. Finally, I'll tie the clock inputs together. I'll just test this quickly. And we do get 5. And it is repeatable. Fantastic! Problem solved. The fix for the unsynchronized reset was fairly simple. We just needed a D flip-flop with a clear input, and we added a second flip-flop to help with metastability. Now we can continue on with the CPU design. But first, let's place this reset synchronizer into a macro like this. And inside the macro, we can see the clock, reset out, and reset in lines connected to pins 1, 2, and 3 of the macro. Again, this is in a counterclockwise direction after backing out. Now, I want to add the automatic reset circuit so that the CPU auto resets during power-up. We've done this before with the Plague Mark I, but this time we already have a reset signal coming into the CPU. So I'll send that into an AND gate, and I'll place an RC reset circuit on the second input of the AND gate, like this. Now when VCC is first applied, the capacitor will look like a short to ground. So this input of the AND gate will be low, which will reset the CPU. As the capacitor charges up through this resistor, it'll slowly pull this input of the AND gate high, which will then take the CPU out of reset. We can't really add analog signals like that in DigitalWorks, but I can simulate it with this here macro that I created. If we go inside of it, we can see that I just sent a clock signal into the clock input of a D flip-flop, and the D input is tied to VCC. In DigitalWorks, D flip-flops always seem to start out outputting a low. Because of this, we can use the output of the flip-flop to internally drive the reset signal low. And then, since the clock starts out as a low, the clock signal will clock a high through the output after the first transition of the clock. We can't do this on the breadboard, since in reality a flip-flop can start up in any state. So this just works in the simulation. Notice that I added the AND gate here, and placed 3 unused gates by the unused inverters, since I'll be using a quad 2-input AND IC on the breadboard. So now I'll set the switches to 2 and run this without first resetting it. And we get 5. I'll try a value of 7 with the switches. I'll release the reset switch when the clock is low. And we get 10, which is 3 plus 7. Then release it on a high clock signal, and you've probably guessed that it still works. Let's try inputting an F, which is 15. Release on a low, and we get 18 as expected. Then release on a high, and of course we still get 18. Beautiful! Let's add this to the breadboard. I'll just place a 74 HCT08 quad AND gate IC right here. Then power and ground, along with the 0.1 mic bypass cap. And first, I'll just terminate the unused inputs. I'll use a 100K resistor along with a 1 microfarad capacitor for the RC reset circuit into one input of an AND gate. Then I'll move the output from the reset switch to the other input of the AND gate. Finally, I'll connect the output of the AND gate to the clear inputs of the flip-flops. Now, before we test this out, I just want to show you a couple quick scope shots of reset during power-up. So I've just powered up the CPU. What we're looking at here is VCC on the yellow trace, which just ramps up to 5 volts. Then the output from the reset switch going into the AND gate is in blue, which almost follows VCC since it is connected to VCC through a 100K resistor. And then the internal reset signal coming from the flip-flops is in pink. And that last trace stays at 0 volts, showing that the system stays in reset right after power-up, even though the voltage from the reset switch rises up to VCC. And of course, the system will remain held in reset until a high is clocked through the flip-flops. Let's look at another scope shot right after power-up. In this scope shot, yellow is still VCC, but the blue trace now shows the charge level on the RC reset capacitor, and it rises up much slower than VCC. The pink trace shows the output from the AND gate, and it stays at 0 volts for a while before going high. We can consider anything above maybe 4.5 volts to be full operating voltage, since HCT logic ICs usually operate from 4.5 up to 5.5 volts. Once VCC gets to 4.5 volts, it takes around 20 milliseconds before the output from the AND gate goes high, which is plenty of time to put the CPU into a power-on reset. Now, of course, this may have been better if I had used a Schmitt trigger right after the RC reset circuit, but this should still do the job just fine. Okay, let's try adding 2 to 3 now without pressing the reset switch first. And we do get 5, so that appears to work. Next, I'll try 7 plus 3. And after a reset, it's 10. Finally, I'll hold them all down for 15 plus 3. And we get 18. Awesome! Now I'm going to take care of this mystery value that the add instruction adds to. So I'm going to finish the add instruction by removing the input switches and connecting the output from register A to the input of the adder, like this. This may seem a little strange, but what it does is allows us to add a value to register A. Now, even though register A has 5 outputs coming from it, I still consider it to be a 4-bit register, so I'll leave the 5th bit unconnected to the adder. I consider that 5th output from register A to be an internal carry flag, and not actually part of register A. We could connect the carry flag to the carry input of the adder, but I'm not going to do that. Instead, I'll make use of the carry flag a little later. In the meantime, we can still use it to see a 5th bit of a summed output. So now, with this slight modification, we can add a series of 4-bit numbers together. I'll write a new program and start out with add 9. This will be kind of like a load instruction, because it will preload register A with the value of 9. That's because register A starts out in the cleared state when the CPU is powered up or reset. Adding 9 to 0 will keep the value of 9. Next, I'll add 3 and add 5 before a halt. Let's put this into the ROM chip. Add 9 is 19 in hex. Add 3 is 13 in hex. Add 5 is 15 in hex. And halt is 80 in hex. So if we run this, we should see 9, followed by 3 plus 9, or 12, then 5 plus 12, which is 17. Let's run it. And we get 9, 12, and 17. Fantastic! Let's try this on the breadboard. So first, I'll reprogram the flash memory with the new program. After IDing and erasing the flash chip, I'll program 19, 13, 15, and 80. Let's dump this out. Looks good. I'll just replace the flash chip. Now I'll replace the outputs from all 4 switches with outputs from the register IC. Bit 0, one, two, and 3. Then I'll just remove this breadboard of switches. Let's give this a try. We get 9, 12, and 17, and it halts at address 3, exactly what I wanted it to do. Now, for the last part of this video, I want to add one more instruction. Since this CPU can now do a little bit of math, I want to create a conditional jump. For the condition, I'll use the carry flag, which is stored in the register IC. When this new instruction is executed, I want a jump to occur only if the carry flag is not set. I'll call this instruction jump if not carry, and I'll abbreviate that as JNC. Since all the bits for the opcodes are now used except for the 3rd bit, I'll use that one, even though we can use more than one bit at a time. And this instruction will have an operand that specifies the address to jump to if the condition of no carry is met. So I'll just mark the operand bits with A's, which stands for address. This makes the hex value 4A. So let's think about how we can execute a conditional jump. We know that we'll need to load a value into the counter, which acts as the instruction pointer. So I'll just remove VCC from the load pin. We're using output number 4 from the decoder for this jump instruction. So we might think to connect that output up to the load input of the counter. Actually, since the load input is active low, we would need to add in an inverter. But doing this will create an unconditional jump. This is not what we want, so I'll just remove that line. We need output number 4 to reach the counter only if the carry flag is 0. We can use one of the AND gates to help us do that. So I'll connect output 4 to one of the inputs of the AND gate. Since I only want to jump when the carry flag is 0, I'll need to invert that flag and send it to the other input of the AND gate. And I'll just use one of the unused inverters to do that. Since we need an inverted signal from this going to the load input, I'll just use another unused inverter to send the output of the AND gate through before connecting it to the load input, like this. Now we should have a working jump if not carry instruction. Let's test it out with some new code. I'll just write a short program that counts from 0 to 20 in increments of 5. To do that, I'll add 5, then jump back to that instruction if there is no carry, and finally halt. What that will do is add 5 to 0, which is 5. Then, since there is no carry, it'll jump back and add another 5, which will make it 10. And again, since there is no carry, it'll jump back and add another 5 until it gets up to 20, which will set the carry flag. and the execution will continue to the halt. The machine code will be 15 hex for add 5, 40 hex for jump if not carry to address 0, and 80 hex for the halt. Let's run it. And we get 5, 10, 15, and 20. Perfect! Let's finish this up by testing it on the breadboard. And like usual, I'll first reprogram the flash chip. I'll just program in 15, 40, and 80 hex. Then dump it. Excellent. I'll replace the chip. So first, I'll take the carry flag output from pin 12 of the register IC and send that into an inverter, and remove the terminating wire from the inverter input. Then I'll remove the terminating wires from the inputs of one of the AND gates and send the output of the inverter to one of its inputs. Then I'll send output 4 from pin 11 of the decoder to the other input of the AND gate, with a shorter wire. Then I'll unterminate another unused inverter input and send the output of the AND gate to that inverter. And lastly, I'll remove VCC from the load input on pin 9 of the counter and send the output from the last inverter to that load input. Okay, time for the final test. We start out at 0, then 5, 10, 15, and 20. Then a halt at address 2. Yes! The beast is coming alive! Ha ha ha! So now I'm about halfway through designing the Plague Mark II. And I mentioned in the first video that it would take about 7 logic ICs to get to this point. Let's count them. 1, 2, 3, 4, 5, 6, and 7. Spot on thus far. So, what do we have at this point? We have a simple CPU that can execute 5 assembly language instructions: no-op, add, out, jump if not carry, and halt. The CPU is contained on these 2 breadboards, and the remainder of the circuit is part of the computer that contains the CPU. Not very impressive, but it does correctly execute the code that we write for it. We still have a ways to go to finish the CPU. We need to complete the implementation of the out instruction, and we need to add a few more instructions. But before we get to doing that, I'm going to veer a little off course in the next video by developing a simple assembler that we can use with this CPU. Right now, we can write some simple assembly code, but we still need to manually translate it into machine code that the CPU can understand. The next video should help automate this translation. And if you're not interested in developing an assembler, you should be able to skip the next video without getting too far off track with the CPU design. Well, that's it for this video. Thanks for watching, and I'll see you next time, right here on Dr. Plague.